Hello, one and all. We will now continue with day 3 of the Summer Teacher Institute on Energy and the Global Environment. And it is my privilege to introduce our next speaker, Seth Darling, who is a scientist at Argonne National Laboratory and fellow at the university's new Institute for Molecular Engineering. After receiving his Ph.D. from the University of Chicago in physical chemistry, he joined Argonne as the Glenn Seaborg Distinguished Postdoctoral Fellow in the Materials Science Division, where he studied directed self-assembly of polymers and polymer nanoparticle hybrid systems. Following his postdoc, Dr. Darling joined the Center for Nanoscale Materials at Argonne as a staff scientist. His group's research centers around polymer molecule engineering, with a particular emphasis on organic solar cells. He also serves as the solar energy strategy leader for Argonne, through which he interfaces with a spectrum of internal scientists, engineers, and managers, as well as external, domestic, and international stakeholders in industry, government, museums, and foundations, national laboratories, market analysis firms, academia, and the media. Finally, I wanted to mention he is the co-author of a forthcoming book titled How to Change Minds About Our Changing Climate. The subtitle, let me get this right, Let Science Do the Talking Next Time Somebody Tries to Tell You ... the climate isn't changing. Global warming is actually a good thing. Climate change is natural, not man-made. And other arguments it's time to end for good. With that, please join me in welcoming Seth Darling.
Thanks. Good morning, everybody. So I will get to solar energy, but we're going to go over some other stuff before I get there. Let me, oh, that's not what we wanted to do. So let's start here. This gentleman pictured on the right is Rick Smalley, or unfortunately was Rick Smalley. He was a Nobel laureate in chemistry. He developed these molecules called fullerenes, or discovered them, I guess, which are useful for all kinds of things, interestingly enough, including solar energy. But he was diagnosed with cancer at a relatively young age, and devoted the last years of his life to looking at the greatest challenges facing humankind over the next 50 years. And after some thought, he came up with this list of the 10 biggest challenges that we face over the next 50 years, and they're actually in order from the top to the bottom. And it doesn't mean that the ones at the top are more important than the ones at the bottom. What it means is that the ones at the top, if you can fix them, it makes it easier to fix the ones at the bottom. So to give you one example, we have a challenge on the planet with unsustainable population growth, but it's been well established that if you improve education in the developing world, particularly among women, birth rates go down. That helps you solve the population problem. So if you can fix this, it helps you fix this. And notice way up at the top of the list is energy. So at least according to Rick Smalley's analysis, energy was the biggest challenge that we face over the next 50 years. And just to give you one other connection here, number 2 on the list you'll see is water. So we have limited and increasingly limited fresh water on Earth. But we don't have a shortage of water, right? We have oceans that are full of lots of water, but it's salty. And we know how to take salty water and make fresh water, desalination. But to do so takes a lot of energy. So if you can solve the energy problem, you can solve the water problem, and so on. So why is energy the biggest challenge that we face? And this is the easiest way to describe why. So this is a plot of the amount of energy we use worldwide. Actually, it's the rate of energy we use worldwide by year. And you'll notice that every year we use more energy than we used the year before. And the units that I'm going to use, by the way, are terawatts. That's trillions of watts, a lot of energy. And if this plot goes back further in time, this keeps going down. And if it keeps further out into the future, it keeps going up for all the way to the year 2100 and beyond. So this is a trend that's not going anywhere anytime soon. And you can see that today, this is data up through 2010, by the way. You see that today we use about 18 terawatts worldwide. And by the year 2035, that's going to be over 25 terawatts. If you take this plot all the way out to the year 2050, over here, it becomes 30 terawatts. So by the year 2050, we'll be using about twice as much energy as we're using today. And you can see where the growth in energy is coming from, primarily because I've broken this plot down. The dark blue is the developed world. That's places like the United States, Europe, Australia. And the light blue is the developing world. That's places like China, India, Brazil, Africa. And as you can see, going forward in time, the developed world is actually not using much more energy. That's because our population is relatively stable and we're basically developed. And in fact, we're tending to become a little more efficient with time. But the developing world is developing. These are folks who were using almost no energy before, and now they're using energy. They have light bulbs and air conditioners and cars that they didn't have before. And so this growth in energy is unavoidable, assuming the developing world is going to continue to develop, which there's no reason to believe it won't. So the question is, where are we going to get all this energy from? Well, let me actually take a step back. Where do we get our energy from today? Fossil fuels. Coal, oil, natural gas is where almost all of our energy comes from. Why? Cheap. Perfect. You guys are good at this. But what I want to spend a little time convincing you of is that those fossil fuels are not actually as cheap as we all think they are. So they look cheap. The electric bill might be low, and I mean, gas prices seem high, but compared to most of the world, they're pretty low. But there's all kinds of other costs that we are paying. We're actually paying. It's coming out of our wallet or purse or whatever for that energy, but it's not going to the electric company or at the gas pump or to People's Gas or wherever you're paying directly for your energy. These are called the hidden costs of energy, and there are many of them, and they're substantial. And I just want to draw attention to this report. This is published by the National Academy of Science. It's available for free online. You can find it. I think it was published in 2010. And what they did is they got together a bunch of smart folks who know about energy, and they tried to quantify how large are these hidden costs associated with the use of energy. And they just took 1 year, the year 2005, because that's what they had good data for. And they only looked at the United States, because it's the National Academy of the United States. In that analysis, they actually ignored some of the largest hidden costs associated with the use of energy. For example, climate change is not in their analysis at all in terms of the number they came up with, not because it's not a huge hidden cost, but because there was just too much uncertainty in the number, and they were trying to come up with a relatively firm number. So they mention it, but they don't put a number on it. They also don't include, for example, national security costs for the billions of dollars we spend securing fossil fuel resources overseas, for example, in the Middle East. So we're ignoring gigantic hidden costs here, but even ignoring those, just in the United States, just the year 2005, the number they come up with in that report is $120 billion with a B. So it's a pretty big chunk of change that's this hidden cost. Now, another thing that people talk about with fossil fuels is that they're a limited resource, right? There's only so much coal, oil, and natural gas under the ground. It was made many millions of years ago, and so at some point it'll run out. But we don't want to wait until it runs out, especially in the case of coal. So oil will probably run out in our lifetime, or at least become too expensive to burn in our cars. But coal, there's probably 1,000 years worth of coal under the ground. So that's not going to run out anytime soon. We can't wait to run out of coal before we start switching. I like this quote. You notice who it actually comes from. It brings special potency to this. This was a Saudi oil minister. And he said, the Stone Age didn't end because we ran out of stones. And he was talking about fossil fuels. He's saying the fossil fuel age should not end because we run out of fossil fuels. We have a better technology. Our ancestors developed better technology than stone, and that's why they stopped using stone. They didn't run out of stones. So we have better technologies available today, and it's time to start moving to the new age. So let's talk about some of these hidden costs. These are the ones that aren't so hidden. These are disasters. And I've got one example here from each of our major energy sources. We've got oil, natural gas, coal, and then nuclear, which would be the next largest energy source today. So these are the things that make the front pages of the paper. In fact, there's a front page of a paper. And there are huge costs associated with these. So petroleum, oil, you have oil spills. The biggest one that has made the news recently was the Deepwater Horizon BP Gulf oil spill. BP had to shell out $20 billion in a settlement for that, but we also all paid for this. We had to send down EPA people, Department of Energy people, Coast Guard, fisheries were damaged. I mean, it's still being evaluated exactly how large the costs associated with this disaster are, but it's certainly in the many, many billions of dollars. But these things happen all the time. Just since this one, there have been spills in the Mississippi River and the Ohio River, all over the place. Oil spills happen all the time. It's just the nature of the business, and there are huge hidden costs associated with that. And those costs don't typically get paid at the gas pump or wherever this oil is going. They get paid through other sources, our tax dollars or other things. Natural gas disasters tend not to be as large a scale as that. Typically, if you have a natural gas disaster, there's a leak in a house and there might be an explosion or a fire in the house or something like that, which doesn't necessarily make the national news. Sometimes, though, they are bigger. This one here is from San Bruno, the part of San Francisco where the airport is. And in this case, a gas main exploded, a 16-inch gas main exploded. And you can see by the time the news photographer got there, it looked like that. You can imagine it was probably worse beforehand. I believe there were actually fatalities associated with this one, but it also destroyed cars and homes, and essentially a neighborhood was destroyed. What that means is that car insurance policies were paid out to replace those cars, homeowners insurance policies were paid out, unfortunately life insurance policies paid out, millions and millions of dollars, right? But none of those dollars were paid on the gas bill that, for the people who lived in this area, right? They were paid by all of us because that's the way insurance works. We all subsidize the insurance for everybody else. Coal, this is very recent. This was just a month or two ago in Soma, Turkey, where they had this big explosion and collapse in the coal mine. I forget what the final number was, something like 200 or 300 miners died in this particular incident. These things also happen all the time, and this one hits home for me. I grew up actually in western Pennsylvania, which is coal country, or used to be coal country. And so I went to school with kids whose dads were coal miners. And I don't know what the economic cost of people dying is, other than, say, life insurance, but I mean, that's a cost, right? It's a societal cost, and it's one that we're paying because we're burning that coal. If we weren't burning coal, those guys wouldn't have been under the ground and they wouldn't be dead. Nuclear, I won't spend a whole lot of time on, but it should be mentioned. There are, of course, disasters associated with nuclear. There are a number of challenges with nuclear energy. Nuclear power plants are potential targets for terrorism. We have to deal with high-level nuclear waste, which we still haven't figured out what to do. And occasionally you have big disasters like this one. So there was 3 Mile Island in this country in the 70s. There was Chernobyl in what's now the Ukraine in the 1980s. And most recently, Fukushima Daiichi in Japan, which was probably the worst of all. And speaking of hidden costs, the estimates are that cleaning this up is going to take about 100 years, and it's going to cost about $1 trillion with a T. So that's a pretty enormous hidden cost. And again, that is not paid on the electric bill of the people in Japan. It's paid really by the global economy. I remember when this happened, like Toyota and folks had to shut down, and so that drives up the price of cars. That's something we all pay for. These are hidden costs. Okay, but the biggest hidden cost, and the one that was not quantified in that National Academy study, is this one, global warming. So we know that putting carbon dioxide in the atmosphere by burning fossil fuels is driving the climate to change. But I want to start with some terminology here. Global warming is a term that I try not to use that much. And the reason is that when you hear the word warming, this is what I picture when I hear warming. It sounds cozy and nice, right? But this is not a nice phenomenon. Yes, the world is warming up, but that's not a good thing. The term that you hear more often these days is this one, climate change, which is a little bit more descriptive. They're actually technically different things, but are used interchangeably in the public. But also, this is not necessarily a great term. I mean, this isn't the right time of year to be talking about this, but here in Chicago, when February rolls around, we're pretty much all ready for some climate change, right? That doesn't seem like such a bad thing either. So the term that I prefer is this one, climate disruption. This is a term that was coined by John Holdren. He's President Obama's chief science advisor and professor at Harvard, smart guy. And I really like the use of this word disruption because it captures the fact that we're taking a system that was more or less stable and we're throwing it out of whack. We're making changes that are too fast for the system to accommodate, and it's leading to all kinds of changes, some of which are not necessarily predictable. And if I may take a moment here, as Andy mentioned, a little self-promotion here. So a colleague of mine at Argonne, Doug Sisterson, he's a meteorologist, a research meteorologist, and I've written this book. I give these talks all the time to the public, and sometimes we get a climate change skeptic in the audience, and you wouldn't believe the variation in the myths that are out there about how it's not happening, or it's not caused by us, or it's nothing to worry about. There's just all kinds of crazy ideas. It's related to cosmic rays. There's crazy things in there. And sometimes I'll get a question and I didn't know the answer. And that would worry me because then everyone else in the room, probably about 5 or 10 of them think that that person might have been right with their question. So I took it upon myself to learn about all these crazy myths that are out there and the science why they're not correct. And we've sort of written all that up into this book. And it's written, there's no equations or anything. It's written for lay folks. So feel free to check it out. It'll come out this summer. It might be useful for your classes as well. Okay, so let's talk about some of these hidden costs. So I spend most of my time out at Argonne National Lab, but I live here in Hyde Park. So I commute out every day on I-55. And I drive past 2 of these things, coal-fired power plants, which were just shut down, thankfully, this last year. But I used to see that stuff coming out the smokestacks all the time. And there's all kinds of stuff in those smokestacks. So one of the things that's in there is sulfur dioxide and nitrogen oxides. And when those things mix with water In the atmosphere, they make acid, sulfuric acid, nitric acid, and that comes down as rain, acid rain. And when acid rain falls on basically anything made out of stone or anything made out of metal, it's going to corrode more quickly than it would have otherwise. So that means bridges, cars, you name it, buildings, all kinds of stuff. So those things have to be replaced and repaired more quickly than they would otherwise because of the acid rain. But that's a cost, right? A significant cost, but we're not paying it to the people burning the coal on the electric bill. We're paying it through other sources. And when we buy a car or repair, tax dollars to repair bridges and things like that, that's another example of a hidden cost. There's also all kinds of poisonous stuff that comes out of there. Heavy metals like mercury, particulates and ozone cause problems that I'll get to in a moment. And then, of course, the biggest thing, the most worrisome, and actually the hardest to keep from coming out of those stacks is the greenhouse gases like carbon dioxide. So where do these things show up as hidden costs? One example would be health insurance. So those particulates and ozone, if you live near a coal-fired power plant and you have asthma, that can cause an asthma attack. And it turns out there are actually tens of thousands of asthma attacks every year caused by exactly this, the particulates and ozone coming out from these fossil fuel plants. Those people end up in emergency rooms to get treated, right? That costs thousands of dollars. But again, it's not thousands of dollars paid to the people burning the coal, it's paid on the health insurance, which we all pay for, so we're all paying for that, but it's a hidden cost. There are connections with things like cancer, developmental disorders. That would be the mercury that comes out of there. It gets bioaccumulated in fish especially, and then if a pregnant woman eats fish that have mercury in it, that can cause her baby to have developmental disorders, which is a lifetime of hidden costs for that family and society in general. Another connection with health is that as the planet warms up, things happen like insect populations, say mosquitoes, start moving to new regions. We're seeing this already in Africa. And what that means is that insect-borne diseases move to new regions. So that's like dengue fever and malaria start going into places where they weren't before. That's a global health cost. I don't know how you quantify it, but it's something we obviously would like to avoid. Food. I already mentioned mercury in fish, but there are other examples of this. As climate disruption proceeds, it causes all kinds of problems with our weather. You get more extreme weather. So it's not that we didn't have droughts and floods forever, but we're going to have more droughts, more floods, and more severe droughts and more severe floods over time because of climate disruption. And these things wreak havoc on agriculture. So just a year ago, the corn crop was devastated by droughts, right? So corn prices went through the roof. I think they actually still haven't come back down. So this is something we're all paying for whenever we consume anything that involves corn, right? So it's a cost that we're all paying for, but we're paying it at the grocery store or at the restaurant or wherever you're getting your food, the school cafeteria, instead of to the people who are causing the climate disruption in the first place. Another example would be ecosystem damage. So this one is what I call the sinister cousin of climate change, of global warming, is water acidification. A lot of folks don't know about this because it's not spoken of in the media as much, but it is a big deal. So we put all this carbon dioxide in the atmosphere, and some of it stays up there, and that's the part that causes the planet to warm up. But a lot of it gets sucked up by the Earth in different ways. Some goes into soil and vegetation and so on, and some goes into the oceans. In fact, quite a lot goes into the oceans. And when you put carbon dioxide into water, you get carbonic acid. And so we're actually making the oceans more acidic over time. You can track the pH for decades now. The pH of the oceans has been going down, becoming more acidic. And that has all kinds of ramifications. One thing that happens is coral bleaching, which is a nice way to say coral dying. So coral reefs around the planet are dying at a rate of about 1% a year. And coral reefs represent some of the most biodiverse places on the planet and are at the base of the marine food chain. So that's a big problem. That's not all caused by climate disruption, but it's a big contributing factor that's stressing them. Another thing that happens with water acidification is creatures that form calcite shells. That's mussels, clams, oysters, things like that. Those shells get dissolved in acidic conditions, so it's much harder for them to grow their shells, which means their populations suffer. And in fact, populations of those types of shellfish are already dropping. The poster child for this would be this guy, the polar bear. It's because the Arctic sea ice is melting at an alarming rate, and those guys need sea ice to survive. And so at some point, they may become extinct. I don't really know what the cost of that is, but it's one example of a species that's really suffering because of climate disruption, and it's at the poles is where you see the effects most strongly and earliest with climate disruption. So those types of effects are going to affect many other species around the planet over time. Now, I mentioned insurance a few times. Other examples are when you have more droughts, it means you have more wildfires. And in fact, we are having more wildfires, and there's just some in the news recently, right? In San Diego area, they were just having a big wildfire. These things destroy homes and schools and businesses. Again, that's insurance policies getting paid out that we're all paying for. Flooding causes insurance payouts, and then a big one would be hurricanes. So we've always had hurricanes, and we'll always have hurricanes. The latest models say that we're not actually going to have more hurricanes because of climate disruption, but they will be stronger, is what's going to happen. And when one of those monster storms hits a populated area, like Hurricane Sandy, Hurricane Katrina as examples, you cause hundreds and hundreds of billions of dollars of damage, often also deaths, unfortunately. And that's going to happen more with time. That's something, again, that we're all paying for, but not to the folks burning the fossil fuels. Now, the last one on this slide, just because I ran out of space, would be water. So I already mentioned one connection between energy and water. There are many. In fact, it's called the energy-water nexus. There are all sorts of different ways that energy and water are connected. Let me just mention a few others. One would be thermal pollution. This is another one you don't hear about as much. But the way these power plants work, coal, natural gas, nuclear, doesn't matter. They're all the same. They're bringing in water, typically from a lake or a river. That's why they're usually located next to a lake or river. And they burn the coal or use the nuclear heat from fission to boil that water and make steam. And that steam turns turbines and makes electricity. But then you're left with that steam. They try to condense most of it, and you end up with hot water at the end, which gets pushed back out into the lake or stream where the water came from in the first place. So what you're doing is constantly heating up the water. And basic chemistry is that as you heat up water, it can't hold as much oxygen in it. So they're depleting oxygen from the water all the time. And what that does is it leads to dead zones in the water because the stuff that lives in the water needs that oxygen. And so they're killing off aquatic ecosystems that way. Now, another connection with water would be sea level rise. So the most obvious way that sea level rise is connected with global warming is that ice sheets melt. So you have this water that's up on continents, and then they melt and it goes into the ocean. So you add water, obviously the sea level goes up. There's actually another reason the sea level is going up that not as many people are aware of, which is that the planet is warming up. And as you warm up things, they expand, right? If you take a balloon and blow a hairdryer on it, it gets bigger. Same thing with the oceans. The oceans are warming up, so they're literally expanding. The oceans are getting bigger, and that means the sea level is rising. It's already risen inches and will eventually rise feet. It's a big problem if you have coastal property, but it's a problem for all kinds of other reasons too, including the fact that a lot of freshwater aquifers are near shorelines. As salt water infiltrates into those places, it's no longer fresh water, and that makes our problem even worse than it would be otherwise. Okay, that's all the bad news. Question is, where can we get our energy from? So what I have here are a series of boxes that are scaled to represent how much energy you could ever get worldwide from these different sources. If you got it everywhere you could feasibly, how much could you possibly get from these different energy sources? Now, fossil fuels, I already told you there's enough coal for 1,000 years, right? So we could power the whole planet on fossil fuels. That's basically what we're doing today. And we could continue to do that in the future. Hopefully that's not what we're gonna do. You could scale up nuclear fission on a huge scale to basically power the planet. But to get to that scale, you would have to build a new nuclear power plant every day, starting today, all the way to the year 2050. That's a lot of nuclear power plants. We haven't built one in this country since like the 1960s or 70s, by the way. And first of all, there's not enough uranium to do that anyway. We'd have to switch to other fuel cycles. But for the various reasons I've already mentioned, maybe that's not what we want to be doing. And then we have over here these renewable energy sources. And the first thing you'll notice is that the boxes are not the same size. Some renewable energy sources are just inherently larger than others. So one that I tend to pick on, not that it's a bad energy source, but geothermal. This is where you're using the heat that's down in the center of the earth. You drill down through the crust and you access that heat and you use it to boil water, make steam, turn turbines, and make electricity. And it's a great energy source where the Earth's crust is very thin and you can actually feasibly drill down to get to that heat. So places like Iceland, for example, get a huge amount of energy from geothermal. But if you look worldwide, how much you could ever get everywhere, it's going to be less than a terawatt. So it's a relatively minor contributor no matter what we do. It doesn't mean you don't do it in Iceland. It just means it's not going to make a big dent in the mix overall. So this is the box that we filled today. This is an 18 terawatt box. That's what I said we're using today. And I asked you where we get our energy from at the beginning. You said fossil fuels. Here's the actual data. The black part of this box is fossil fuels. And you can see that it's almost the entire box is almost all of our energy is coming from fossil fuels. This is nuclear and hydropower would be the next two, and then almost nothing from these other energy sources. But I'm not so much concerned about today, not because it's not a problem, it's just we can't do anything about it, right? That's what it is today. My question is, I have an 11-year-old. What about when he's middle-aged in the year 2050? What are we gonna be doing then? So now we've got a much bigger box, right? The year 2050, it's gonna be 30 terawatts is the projection, again, because the developing world using more energy mostly. And what's our energy mix gonna be in the year 2050? And if you ask the folks who project these things, like Energy Information Administration and other organizations that try and project this stuff, this is kind of a consensus of what that energy mix is going to be in the year 2050. So first thing, this is a little bit surprising, because if you don't really pay too much attention, it kind of looks just like the last slide, right? Now, everything got a lot bigger, because it's almost twice as much energy, but it's still almost all fossil fuels all the way out in the year 2050. In fact, this is a huge growth in our use of fossil fuels, not using less, but using more is the path that we're on. Now, these guys all got a lot bigger than they were, but because everything got bigger, it doesn't really matter. This is not an acceptable scenario, primarily because of climate disruption, but also all the other hidden costs that I mentioned. So the question is, what can we do? What are our options? So let's just say hypothetically we didn't want to use any fossil fuels in the year 2050. And I'll tell you right now, we will almost definitely be using fossil fuels in the year 2050. So that's not really realistic, but just hypothetically, let's say we didn't want to use them. And let's say we wanted to avoid nuclear for the reasons that I mentioned earlier. How much could we get from those renewable energy sources over there? So if we get all the wind on the planet everywhere we can, all the geothermal, all the hydropower, and so on, empty those boxes out, how much energy could we ever get from those sources? It's about this much. You'll see we're coming up pretty short here, right? We can't power the planet just with wind and biomass and hydropower and oceans and geothermal. You'll notice, though, if you're paying attention, that there's one box that I didn't show you yet, which is solar. So the question is, how big is that solar box? So I told you I'd get to solar energy eventually. So now we're going to switch from boxes to circles. This is a circle. It's just too big to fit on the screen. And what that is the amount of energy hitting the surface of the Earth from the sun all the time. And it's a huge amount of energy. It's actually, solar energy researchers like to throw out the statement that there's enough energy from the sun hitting the Earth in 1 hour to power the entire planet for a year, which is technically correct, but it's also not a very helpful statement, because of course you can't capture all of the energy hitting the surface of the Earth. So what this is kind of a back-of-the-envelope estimate for what's feasible. How much could you actually get? So the first thing I'm going to do is throw out the oceans, because it's really not feasible to put panels all over the oceans. So we're scaled down by land area. But you also, of course, can't cover all the land area with panels. You need farms and other things on the land. What's a realistic amount of land to cover? I'm going to say 2%. So just to give you a sense for what 2% looks like, it's like that. Not that we're going to put all the panels in west central Kansas, but that's 2% of the United States. It's a lot of land area. That's about the amount of land area covered by roads in the United States, to kind of give you a picture in your head what would be needed. But it's feasible. We could do this. Now, there's another problem, though, which is that you can't convert sunlight to electricity with 100% efficiency. There are fundamental losses in that process. So the best you can do with what I'll just call a normal solar cell, a single junction solar cell, is 30%. Laws of thermodynamics limit you to that, right about 30%. I'm going to make a much more conservative number of 12%. By the way, you can buy panels for your roof today that are 20%. A company called SunPower makes 20% commercial panels that you can put on your roof today. So this is a very realistic number for an average conversion efficiency. And you'll see that this circle that we're left with is a pretty miserable fraction of the one that we started with, right? But that tiny little circle over there is that yellow box. So the feasible supply from solar, what we could really get, is more than 2 times larger than the total projected global energy demand all the way out in the year 2050. And in fact, it's bigger than the total projected demand in the year 2100. So this is essentially an unlimited energy source for us. It's more energy than we'll ever need is available from the sun. And I don't say this to say we should get all of our energy from solar energy. That would actually be a bad idea. You want an energy mix for energy security reasons, because the sun doesn't shine all the time, for example. But it needs to be a much bigger piece of the energy mix than it's projected to be even out in the year 2050, which would represent a huge growth, but not enough. It's got to be a much bigger piece than that, because it's the only one that can be. Doesn't matter what you do with these other sources. If you get them everywhere, they're not enough. You do that, it's just not enough. And by the way, it's not that surprising that these other energy sources are smaller than solar, because they really are solar energy in disguise. So the wind happens because the sun heats up the air and it causes convection and other things that moves the air around, and some of that wind you can capture with turbines and get energy out. So that's going to be smaller because it's going through extra steps. Biomass, that's plants taking sunlight, making chemical fuel through photosynthesis. Again, extra steps. Hydropower is the sun evaporating water. It goes up to a higher elevation, rains down. Some of that comes down mountains where you can build a dam and get hydropower out. So all of these things are really solar power going through extra steps, which is why they're smaller, feasible supplies overall. It makes a little more sense to go for it straight from the sun most of the time. Okay, so what are our options today? There are basically 3 types of solar panels that are available today. 3 materials that they're made out of: silicon, cadmium telluride, and SIGs. This stands for copper, indium, gallium selenide. And each of these technologies has advantages and disadvantages. So silicon is the vast majority of the market. Something like 80 to 90% of the panels out there are made out of silicon. And there's some great things about silicon solar panels. First of all, there's a lot of silicon on the planet. So sand is silica, right? And in fact, that's where it comes from, is quartz sand is where they get the silicon that they use in silicon solar panels. So we're not gonna run out of silicon. They're also very efficient. So those 20% panels that you can buy for your roof, those are actually silicon solar panels. But there is a challenge with silicon solar panels. Anyone know why? What the issue is? Why we don't all have them on our rooftops? I'm assuming you don't all have them on your rooftops.
Heavy?
No, expensive. They're expensive. And the reason they're expensive is that to get an efficient silicon solar cell, you've got to make it crystalline and extremely pure. That means you have to go through some purification steps and melt silicon, which you can imagine is a pretty high temperature process. That takes a ton of energy. Energy is money, and so these things are expensive. And the costs are coming down over time as we get a little better at it, but they can only come down so far because there's a whole bunch of energy in there, and I'm gonna get to that more in a moment. Now we have two technologies that in principle are lower cost, but these have issues as well. So cadmium telluride has two problems, cadmium and telluride. Cadmium is a toxic heavy metal, like mercury. It's not gonna hurt you while it's sitting in a solar panel, but you've gotta extract the material from the earth, process it, manufacture the panels, recycle them at the end of their life. These are all ways in which cadmium could get out into the environment, would not be a good thing. Telluride is referring to tellurium, element on the periodic table. Turns out it's also toxic, more toxic than cadmium. But that's not the big problem with tellurium. The problem with tellurium is that it's one of the rarest elements on the planet Earth. So right now there's not a big demand for tellurium, so the people making these panels have plenty to make them. But there's just not enough to get terawatts of energy from cadmium telluride solar panels because there's not enough tellurium. It's basically the end of the story. It's a good stopgap technology, but it's not gonna make a big dent in the energy mix. And then we have the same problem here. Indium and gallium, the ING, are also rare elements. The cost of indium is already going up. It's used in flat panel displays because it's used in transparent conductors. So these costs are gonna skyrocket, and this technology will eventually not be feasible either at a really large scale. So we kind of feel like we're stuck here, right? We have two technologies that never really could be scaled up, and one that seems like it's too expensive because it takes so much energy. Let me get to that energy point here. So when you make a solar panel, you have to invest a certain amount of energy into that process. You've got to mine the material that you're using out of the earth, you've got to process it, you got to run the factory that manufactures it, you got to ship the things from point A to point B and so on. You put all this energy in, and then you plug it in your home or business or wherever it is, and it starts giving you energy back. And the question is, how long does it take you to give the energy back that you put in? And it better be a shorter amount of time than the lifetime of the system, otherwise the whole thing was kind of pointless, right? So typical silicon solar panels that are commercially available are guaranteed for 25 to 30 years. Often they'll last much longer than that. And the payback times for silicon solar panels are about 2 years. So that's good, because you'll get back a lot more energy than you put into making the thing. But 2 years is a long time. And if you want to scale up to make terawatts of energy from solar, so huge, huge growth compared to where we are today, you'd have to invest a huge amount of energy to make those panels. And where are we going to get that energy from? We don't have that energy today. That's the problem, right? We're trying to make the energy. And so you actually cannot scale up silicon solar panels fast enough to make a huge dent in the energy mix because it takes too much energy to make the darn things. Now, as they become more efficient, as we get better technology and make silicon solar panels better and better, the energy payback time gets shorter because a more efficient cell gives you back the energy faster, right? But even if they get as high as they could ever be, so 25% is the best you can do with silicon just by the laws of physics, basically, you can see you're still talking about like 6 months. And we're a long way from this point anyway. So there are different types of silicon, some of which have slightly faster energy payback times, but we're still talking about months to years. Cadmium telluride, you can see, has faster energy payback time. It takes less energy to make these panels. Although we're still talking about months, and anyway, there's this issue that with the tellurium, you just can't get terawatts of energy from this guy in the end anyway. But there are other technologies on the horizon. So one that was mentioned by the previous speaker, I heard dye-sensitized solar cells. That's one example of a next generation technology people are working on. Another one will be organic photovoltaics. This is actually what we do in my group. This is an organic solar module here. So first thing you'll notice is that if you've ever seen a solar panel, it doesn't look like this, right? They're heavy, as you mentioned, and big and rigid and made out of glass and bolted on a rooftop. And this is not heavy and not rigid. But this is a solar panel that works. I've got the electrodes covered so nobody will get electrocuted. So we can pass this around, but that purpley color you see on there is a blend of a polymer and a fullerene, Rick Smalley's molecules, which work just like silicon. They absorb sunlight and give you electricity. The cool thing about these materials is that you can take that polymer and fullerene and put them in a solution and print or coat them on a surface in a roll-to-roll process. So you can have a roll of silicon, or a roll of plastic on one side that runs through a machine like a newspaper, gets printed really fast, gets laminated, comes out on the other side, you have a solar panel. Really low cost, very low embedded energy, and you can see that here with the energy payback times. So the efficiencies on those are much lower than silicon. That one right there is like 1% to 2% efficiency. You can see even at that really embarrassingly low efficiency, it already has a faster energy payback than you could ever get with silicon. And if you can push those efficiencies higher, say 10%, which is, by the way, what we can do in the lab on a cell, so if you can scale that up to a module, you're talking about energy payback times measured in days. This is something that is just unachievable with any of the existing technologies, and this is really what you need for a solar technology that can be scaled up. Question?
I didn't understand the second word, polymer and.
Fullerene is the word. It's a carbon-based molecule that looks exactly like a soccer ball. You can Google it. Very cool molecules. They're useful for all kinds of things, including this. Okay. So this is kind of what we do at Argonne National Lab, is I told you the materials that are currently available for solar panels are not going to cut it. We need new materials, right? One of which, one example would be organic photovoltaics. So you develop these new materials, you put them into a solar cell, and you optimize that process and make yourself an efficient solar cell, but you can't stop there. That's where an academic laboratory would typically stop, and you can get lots of papers and become a famous scientist, but you're not changing the world, right? You're not changing the energy mix by making a little solar cell that's efficient. What you need is thousands or millions of these things. You have to scale it up. And scaling up from this to that is called process engineering. And oftentimes you're going to need to rethink your materials so that they're scalable and that the process itself is scalable so you can really do this. And then once you've optimized that process, then you can roll that technology out to the commercial market, give it to the people who make and sell stuff, and let them do their thing. So one example of a technology where we're trying this is organic photovoltaics, and others would be dye-sensitized solar cells, and there are plenty of others that people are exploring as well. And by the way, this is something that Argonne has done with batteries, just to show you that this approach can work. So a little more than a decade ago, colleagues of mine at Argonne developed new materials for the electrodes in lithium-ion batteries that worked better than what was available before. They made little test batteries and optimized that process and made them really nice, but they didn't stop there, right? They looked at this scale-up issue. How do you go from this to making tons of this stuff? And optimize that process. And today, those batteries are in things like the Chevy Volt. If you see a Chevy Volt on the road, it's got Argonne technology in its batteries. So this has been done in batteries. The idea is to apply that same methodology to solar energy. Okay, now one more thing before I wrap up that always comes up when you talk about solar energy and also with wind, and I mentioned it earlier, is the fact that the sun doesn't shine all the time, right? And the wind doesn't blow all the time. Now, people in the traditional energy industry, especially the fossil industry, will try and tell you that that means that it's hopeless, right? You can never have more than 5 or 10% of your energy mix coming from solar and wind, because otherwise you'd have blackouts all over the place and it would be disasters. That's not true. There are lots of things you can do to accommodate variability in supply. I'm not going to go through each of these, but these are all different strategies that can be used. I'll mention just a few of them. One would be forecasting. So right now on the grid, a lot of people don't know this, but there's stuff called spinning reserve, spinning power. These are power plants that are running all the time and dumping their electricity. It's not being used. And the reason they're doing that is that demand can have spikes in it, right? We all go home from work and it's a hot summer day and we turn on our air conditioner and all of a sudden there's this big spike in demand and we don't want there to be a blackout because this is the developed world and we don't like that kind of thing. So they have these power plants that are running that they can just rapidly pull the power off. And those plants, of course, are burning fossil fuels. They're typically natural gas power plants, and so that's causing a lot of the problems that I discussed at the beginning. Now, if you start throwing variability on the supply side instead of the demand side, because the sun, you might have a cloud, the wind might stop blowing, so now we have variability not just because of a spike in demand, but maybe a drop in supply. Then you might need a lot more spinning power to deal with that, right? But firing up one of those spinning power plants takes something like 20 minutes or so to power up one of those guys. So if you know 20 minutes ahead of time that there's going to be clouds, or 20 minutes ahead of time that the wind is going to stop blowing, you can fire it up just then instead of having it running 24/7. And so what we need is better forecasting. This is possible, it's just not set up to do this today. If you have better forecasting with sort of that 20-minute notice, you can deal with this without having to run those spinning power plants all the time. Another example would be a smarter grid. So maybe the sun isn't shining here today, although it is. Okay, so we'll turn it around. The sun's shining here today, but maybe it's cloudy down in Indianapolis, right? So if the grid was set up that way, we could move power from solar plants that are up here down to Indianapolis. Or maybe the wind isn't blowing here, but it's blowing in North Dakota, so we can move the power from the wind plants from there to here. Right now, the grid is not equipped to move large amounts of power around large distances like that, but it could be. There's no reason it couldn't be. We just need a smarter grid. And so that's also something we're gonna need to do. The biggest thing we can do is this, storage. So yes, the sun doesn't shine all the time, but actually during the day, on a really sunny day, almost all solar power plants are generating more power than they can use. There's excess energy coming out of these things. So if you can save that energy and use it later, at night especially, or when the cloud comes over, that can even out the generation side. And there are lots of ways you can store energy. One way would be batteries. You can have these in your house. You can actually buy these today. They're sort of sized like a washing machine, and you can power them up with the solar panels on your rooftop, and then at night pull them down, pull the power down. Another thing where you can, battery source would be electric vehicles that I mentioned earlier, like the Chevy Volt. Once more of us are driving electric vehicles, like most of us, and some percentage of those are gonna be plugged in all the time, right? Whether they're at work or at home or wherever, some percentage are gonna be plugged in. That's a huge array of batteries that are plugged into the grid, which could be used as basically power backup. You wouldn't want to drain everybody's car and then you can't get to work, but maybe 5 or 10% of the battery could be used for this storage purpose. And of course, then it would charge it back up when there was excess on the grid, and the company would pay you when it pulled the power off. So that would cost us almost nothing to do it that way, right? That's one strategy. Another way to store energy is thermal storage. So this is actually available today. I've talked a lot about solar panels, photovoltaics, but there are other ways to use solar energy to make electricity. One of those is called concentrated solar power. This is a commercial thing that's available today. What they have are arrays of mirrors, typically parabolic trough mirrors, that focus the sunlight onto a tube that has a fluid in it, generally a molten salt. And it gets very, very hot, like ant on sidewalk with magnifying glass. And that molten salt runs through a system, and normally it would go through a heat exchanger to boil water, to make steam, to turn turbines, to make electricity, just like a coal-fired power plant, but the heat comes from the sun instead of from burning coal. But if you don't need that energy right now, what you can do is hold on to that heat. That's really easy, right? A big, giant coffee thermos, basically. You have this huge, thousands and thousands of gallon container that's insulated, and you can hold on to that heat for hours and hours, all the way through the night, easily. And then you can just generate it whenever you need it. So that's a way to turn variable solar energy into nice baseload power. Lots of strategies are available. So let me just end with this. If you go to this URL, you can find much more technical detail than I went into today about some of the projects we do at Argonne in the area of solar, as well as a little bit of the background information that I talked about. And we've got about 15 minutes or so. I'd be happy to answer any questions you have now. Yeah. So what that is something called building integrated photovoltaics, BIPV, which is one way to use solar energy. So you can put panels on a roof, or you can make the roof a panel, which is basically what you're talking about. So there are a couple companies that have come out with shingles that are actually solar panels. So they have sort of a bluish color because they're made out of silicon or other technologies. And those can be, you don't need organics to make that type of panel. It can be made out of all kinds of different technologies, including any of the 3 that I showed you. There are advantages to using technologies like these because these can be used in places where you wouldn't use traditional panels, like, say, a window. You can make a window, first of all, you can make these any color you want, which is another advantage, which you can't do with silicon. Silicon panels are always blue. These can be any color you want by playing with the spectrum. But they can also be semi-transparent. So you can actually make, it would look like a tinted window, basically. So some of the light comes in, and in fact, it can block things like the infrared part of the light, which would be heating up your house in the summer, so you don't need as much air conditioning, so that's a passive way to use the solar energy. But it would be pulling off some of the energy and turning it into electricity as well. You would never do that with a traditional solar panel because they can't be made transparent. They can also go on walls of buildings. So this technology works much better in low light conditions than a traditional silicon solar panel does. So silicon solar panels, you want angled right at the right angle to capture the most direct sunlight as possible. And sort of in the dawn and dusk, they don't even give you any electricity because the light level's too low. This guy works beautifully. Like right now, even in this room light, that would be generating electricity. And so you can put them on sidewalls of buildings which have lower light levels. You can imagine like the Willis Tower, the whole side of that guy being solar panels. You would never do that with traditional ones, but a technology like this, you could. So this technology, that's another challenge with it. One is the efficiency, which we're working on. Also, their lifetimes are not as long as the silicon solar panels. So this thing, if it sits in my office, will last a very long time. It's been in my office for years, and it works pretty much as well as the day when I got it. But if I put it on the rooftop here, it would die probably in a year or less. And the reason is that that thing is laminated, just like a piece of paper, right? And when you have freeze-thaw cycles, like we have in Chicago here, and heavy precipitation and all of this, eventually water and oxygen find their way inside. And both of those guys are trouble for the organic molecules as well as the electrodes. So we need are better ways to keep out the oxygen and water. That's actually something also that we work on at Argonne and other people work on as well. So the lifetimes now, depending on where you put it, it would last longer in Texas than it would here. But like I said, are sort of year, 2 years, something like that. You really want to get that out to be like 10 years to be commercially viable. And I think we'll get there. We're just not there yet today.
And are the little octagon-shaped balls, are those like bucky balls?
The octagon-shaped balls.
The organic material that's inside. I thought you said something
Yes,
about the
it's a molecule that
octagonal
looks, I mean, it literally is exactly the same geometric shape as a soccer ball. It's like made up of hexagons and pentagons, just like a soccer ball is if you look at one. It's carbon atoms doing exactly the same thing. That's a fullerene.
But isn't that what they call bucky balls?
Yeah,
After
they're called
Buckminster
Bucky balls also.
Fullers?
Buckminster
Yeah, okay.
fullerene. Yeah, fullerene is short for Buckminster fullerene. The architect who built things like that, yeah.
I was wondering, for Argonne integrated approach, which stage are you with solar?
Well, it depends on which technology you're talking about. So with organics, we're really looking at how to scale up. So in my lab, typically what we're making are cells that are literally only this big.
Okay.
And you can learn all kinds of stuff from that. But you can see we also deal with panels that are this big. And we're really working hard on understanding what are the losses when you go from this to this. Why is this close to 10% and this like 1%? And by the way, this isn't something we're only doing at Argonne. There are hundreds, maybe even thousands of labs around the world studying organic photovoltaics and lots of other next generation photovoltaic technologies. And there are some that focus exclusively on that question about this real scale up. There's this wonderful lab in Denmark at the Dutch Technical University where they are doing exactly that.
At the end of your diagram, you had the commercial arena. Are there commercial partners that you work with, or are there NGO partners that you work with to take this technology out to reality?
So in my group, we don't currently have an industrial partner. We actually, that's not true. We're working with a glass company. Turns out there's, if you make glass really, really thin, like really thin, 100 microns, it becomes flexible, like plastic, and it won't break. It's really amazing to see. And the cool thing about glass is that it's impermeable to oxygen and water. So you can see where we're going with this. You could possibly, instead of using plastic, use flexible glass, solve the stability problem that we were just talking about. So we're working with a glass company on that project. But there are a few companies out there that are trying to make money by exploiting this technology. It's a tough market right now. Energy in general is a really tough market because energy is a commodity. You want to pay a certain number of cents per kilowatt hour of electricity, and you don't care whether it was made from a solar panel or coal. I mean, maybe you care, but your typical consumer doesn't care that much. And so you've got to compete on that really harsh market. And it ain't easy, because those hidden costs aren't included in there. And solar tends to be more expensive if you don't include the hidden costs. So this panel right here was actually made by a company called Konarka Technologies, which was in Massachusetts, founded by a different Nobel laureate, Alan Heeger, his technology. They unfortunately went bankrupt about 2 years ago because they just couldn't, it was too early, is what it comes down to. So there are companies that are trying. There are some other ones, Heliotech and some others that are out there now that are trying. But I think the technology is not quite to the point yet where it's ready to be commercialized.
Andy's got me trained. I heard somebody in alternatives, and it might have been solar, say that they didn't need money from the government. They just needed the government to stop subsidizing oil and fossil fuel to
Yep.
level the playing field. How much would that be enough to get you all off and running?
Okay, so I have to start with a caveat, which is that I'm not a policy expert, so I want to be careful. Also, I work for a national laboratory, so I have to be careful talking about policy. But yes, there's a nice report, another free report you can find online called What Would Jefferson Do?, which is put out by an investing firm, interestingly enough. I think they're called DBK Investors or something like that. And what they did is they evaluated historically subsidies for different energy sources all the way back to the beginning, more than 100 years ago, all the way up till today. And they put it into constant dollars, because obviously, a dollar 100 years ago is not the same as a dollar today. And they compared, how has the government subsidized coal versus nuclear versus renewable energies. And it turns out that the renewable subsidies that we hear so many complaints about politically today are actually smaller than any of the subsidies that have been given to any other energy source historically. It turns out to change energy sources, you just need a push, and that push has to come from subsidies, and that's what got us nuclear going back in the 60s or so. And it's what we need today for renewables, and it has helped, right? I mean, there are plenty of places in the country today where it's cheaper because of subsidies to put solar panels on your house than to pay on the grid. And so those places are going crazy with installations. Hawaii is the best example of this. Electricity is really expensive in Hawaii, and there's lots of sunshine, so it's a great place for solar. And so many houses are putting on solar panels there that it's becoming a problem for their grid because they don't yet have the smart grid and all these other advantages that we need that I talked about. Many of those subsidies for the fossil industry are still there. It's not like they came and went away. So many of them are still there, and they're in weird forms like tax breaks and things like that that aren't direct subsidies like you see for solar, where here's $3,000 from the state to help you put panels on your roof. It's not quite the same with something like coal. They're more subtle with things like tax breaks. That report I mentioned goes into a lot of those details. Well, right. So I mean, all these hidden costs. Again, we're all paying for these, right? If that cost was put in front of the consumer visibly, then we would choose the cheapest option, right? Because we're not stupid. We're going to go with what's cheaper. Right now, the coal looks cheaper because we're not looking at all those hidden costs. If you put those in front of people, suddenly now these renewables look a lot cheaper because they are. And there's ways to do that, to put that cost in front of the consumer. One way is a carbon tax. That's a direct way to do it. Another way would be a cap and trade system. Yes, that makes those energy things cost more. You would pay more on your electric bill, but you're already paying more. You're just paying it somewhere else, right? It would just be a way to show you where your money actually is going, and now you could make the right economic decision and go with the renewable energy.
I'm just curious about your level of optimism. When you look at the problem, the data you presented earlier in your talk, it's fairly daunting in terms of the problem, but toward the end, it's very exciting. So where are you at in terms of as you assess all of this?
So I wouldn't be working on it if I didn't think it could be fixed, right? But it is daunting. And there's a quote that I like from another solar energy researcher. His name's Dan Nocera. He's at either Harvard or MIT. I forget. He was at one and went to the other one. I can't remember where he is now. But he does solar fuels research, which is another type of solar energy. Anyway, he came to Argonne and he gave a talk, and he was asked basically the same question. And what he said is that as a scientist, it's your obligation to go down swinging, which is that the idea is that, in principle, we can do something about this, right? There are technological solutions to this problem. It's the scientists and the technologists who can develop those technologies. So even if we think the chances are low that we can get there in time, it's our obligation to try and do it, right? So I'm a technology guy. That's what I can fix. There's plenty of other ways to attack this problem. Policy is a great example. And so hopefully there are lots of folks out there who are motivated to push on that side as well.
I actually have a question, and it's this. So your presentation is amazingly hopeful in terms of sustainability, and it's something that I really value and appreciate. But in the back of my mind, I was also wondering how these technologies might be able to address issues of energy access. So as your graphs show, we expect that there'll be increasing energy consumption throughout the so-called developing world. And of course, a significant amount, over 1 billion people, do not have regular access to basic energy, electricity, et cetera, worldwide. Do you feel that the affordability, the portability of some of these technologies might be able to address some of those issues?
Yeah, absolutely. So the way that we use our energy has been developed because of where energy was coming from. It came from coal. Well, if you go way back, it came from wood, right? And everyone would chop down their own wood and make their energy in their own house. But then we had these coal, and you can't have everyone have a coal-fired power plant in their own house. So we built these big power plants, right? Centralized power, and then would spray out the power from there into all the surrounding neighborhoods or cities. I view sources like solar as kind of the re-democratization of energy, right? We can start generating our own power again by putting panels on our own rooftops, which does free us up from that reliance upon the centralized utility companies, and obviously utility companies don't like that. Also, it gives the grid greater resilience. If a power plant goes down because of some failure, you got, 100,000 people who have blackouts because of that. Something happens with the solar panels in someone's house, it's just that house that's affected, right? It gives you more stability to the grid. Also, something we have to consider today is terrorist attacks, right? Power plant's a great thing to go after, right? Because you would affect so many people. But if everyone's generating their own power, that becomes a pretty poor target. Now, in terms of accessibility in the developing world, there's a wonderful project, which I think is still going on, called Lighting Africa. So I talked about those 10 problems at the beginning, right? And education and population and things like that were on that list. And one of the challenges in the developing world in places like sub-Saharan Africa, where there's no grid at all, people don't have lighting when the sun goes down. And so students can't do their homework. They can't read. They can't be educated at night unless they're using a candle or something like that. So this whole project was designed to come up with a very robust and low-cost system that would put together a solar panel and an LED light source, an LED lantern, so that you could charge, and a little battery, and you'd charge this thing up during the day, plenty of sunshine in sub-Saharan Africa, and then run this lantern at night. And there was a competition to see which people could develop the lowest cost, most robust system, and I haven't really followed it to see what came out. But that's a good example of the kind of thing that you can do with solar that you can't do with traditional energy sources.
Just going back to the beginning where you were looking at the power plants, that they're in Pilsen, the one that was shut down, and Pilsen has some of the highest asthma rates in the country, probably because of those power points. So because of those power plants. So on top of like health and human loss and everything else, a huge loss of productivity. I don't know how many of our students are missed days because they have asthma. I've never seen so many kids with asthma, and it really struck a chord.
Absolutely, yeah. I mean, these hidden costs, I could spend 5 hours going through all the different hidden costs. They're innumerable, and some of it's economic costs, some of it's productivity, some of it's just human suffering.
Just in the interest of teaching this, I've used for a few years that film, a documentary called Saved by the Sun, and they mention painting on, it's almost like a fiber optic, but I believe it's even a nanotechnology, painting on solar panels essentially on the roof. Is that related in some way?
Yeah, so people have been talking about solar paint for a while, and the technologies that you would be talking about would be things like this. So as I told you, you can put these materials, that's what we do, is we put them in solution, and you make it an ink, basically. In fact, we call it an ink, which can be coated or printed on a surface, or in principle could be brushed on a surface like paint. The challenge today is that, as I said, they're sensitive to air and water, and so it's not as simple as just slathering the stuff on your rooftop and you have a solar panel, because you got to be able to keep out the oxygen and water, so you need more of a process, some way to seal it. So today there isn't such a thing, a really feasible solar paint, but maybe down the line we'll be able to get to something like that.
Do you know of any more up-to-date documentaries that might?
I don't, and in fact I haven't seen that one, so I'm going to look that up.
It's very good. It's a really nice explanation for kids and adults as well, and it's entertaining and has a lot of historical pieces.
Yeah, I will check it out. Unfortunately, I don't know another good documentary.
What would you suggest is something realistic that everyone in the room could do relative to solar energy? That we could teach our children, that we could talk to our friends about? I mean, is there anything realistic that you've implemented yourself, or that you feel is a good investment for homeowner, apartment dweller?
Yeah, so I would say, first of all, not just solar. I mean, it's really energy holistically is what we're talking about. I happen to be a solar energy researcher, and solar has to be, as I said, probably the biggest piece of the puzzle, but it's not the answer, right? We still need wind and biomass and hydropower and all these other sources at once, and some nuclear and some fossil fuels as well. So I don't mean to say like we should all be doing solar. It just needs to be a much bigger piece of the story than people have been talking about. In terms of what you can do, so I give a lot of talks to schools, and high school students in particular. Often, the question I often get is, I'm not going to be a chemist or an electrical engineer or a material scientist or whatever, so how can I impact this problem? And my answer is most often policy, right? The biggest challenge we have here is that these hidden costs are not put in front of people. We need that to happen, and that doesn't happen until there's a groundswell of political pressure for it to happen. And you need smart policies that strategically attack the problem in the most efficient way, and you need enough political support to get those policies put in place. And so that's really where I think your typical everyday non-scientist, non-engineer person can make the biggest impact, is by understanding that first, and then also spreading that message in every way, voting, talking to your friends, all the different ways that stuff can happen. In terms of physically on your own home and what you can do, of course, you can buy solar panels and put them on your rooftop. it's actually reasonably cost effective, more so in some parts of the some parts of the world than the others, where there's more sunshine, electricity is more expensive. So New York City, California, places like that, where there's really high electricity costs, it's a no-brainer. You should just put panels on your roof. Here in Illinois, it's not quite as clear because we have a little less sunshine and our electricity is kind of cheap here. So it would be more of a, I mean, you get the payback, but it would be years down the line. So it'd be more of a moral decision or a environmental sustainability decision than an economic decision to do something like that. And by the way, there's things you can do other than panels. You can heat the water for your house with these hot water heaters that go on rooftops. There are parts of the world where almost every house has these. Israel, almost every homeowner has one of these things on their rooftop. It just uses the sunlight to heat up the water, and they don't have a hot water heater in their basement. And so their hot water heating bill is zero. They just have to buy the system up front.
Well, let us thank Seth Darling